The South China Sea at 2:33 a.m. is a body of water that does not announce itself. No landmarks, no coastal references, no visible horizon in the overcast, just the dark surface running a 1-meter swell from the northeast. The sky above it, a uniform gray that absorbs radar energy differently than clear air. And 3,500 meters of water column beneath the keel in the basin southeast of the Pratas Islands. USS Dewey makes 22 knots on a southerly heading, threading the median corridor in a region where the difference between international waters and contested space is always a matter of attention. She has been on station for 7 days. The People's Liberation Army Navy has had surface contacts on her since the Luzon Strait 4 days ago. The observation is continuous and professional. It is also, as of 2:29 a.m., no longer passive. The EW operator classifies the Fujian Coast Battery's radar mode shift at 2:29 a.m. Active targeting mode, consistent with a YJ-21 hypersonic anti-ship missile system. He reports it in 6 seconds. The Dewey's Aegis goes to full active engagement mode. The combat systems officer begins building the intercept geometry. The VLS operator confirms cell status. The watch team has been at general quarters for 30 minutes. The targeting radar shift was preceded by a period of unusually dense PLAAF activity overhead, which the officer of the deck interpreted correctly as a preparation phase and ordered GQ accordingly. The team is ready. They have a targeting radar acquisition and approximately 9 minutes to first missile impact at YJ-21 flight speeds. 9 minutes is workable. The Dewey's engagement sequence against a YJ-21 profile has been drilled. 2 SM-6 missiles, staged intercepts. The second engagement serving as insurance against the kinetic penetration capability of the hypersonic vehicle's terminal phase. The math is within parameters. The YJ-21 launches at 2:31:14 a.m. The SM-6 assignment is immediate. The first SM-6 leaves the VLS at 2:31:40 a.m., 26 seconds after launch detection. The second SM-6 follows at 2:31:52 a.m. Both track files are solid. The engagement is running correctly. The first SM-6 intercepts the YJ-21 at 62 miles. The proximity fuse detonates. The expanding rod warhead detonates at a range of 11 meters from the YJ-21's airframe. An outstanding intercept at that closure rate. The YJ-21's airframe is not intact. It is disrupted. A hypersonic vehicle at Mach 6 with 11 meters of separation from a warhead detonation absorbs the blast energy and the fragmentation pattern. And the result is a vehicle that loses aerodynamic stability, sheds heat shielding panels in a cloud of debris, and continues forward on a ballistic trajectory. Still moving at Mach 5.4 on a terminal bearing. Still generating a 400-meter wide bow shockwave at that velocity. The second SM-6 tracks the disrupted vehicle and engages at 21 miles. A proximity detonation within 6 meters that finishes the aerodynamic disruption and separates the warhead section from the propulsion section. The warhead section tumbles. The propulsion section continues forward. The propulsion section of a YJ-21 hypersonic vehicle at Mach 4 and 21 miles from its target has approximately 14 seconds of time of flight remaining. It cannot be guided. The terminal seeker is with the warhead section, which is now spinning in the water 40 miles away. But the propulsion section has mass, approximately 340 kilograms, and velocity, and 14 seconds of Mach 4 flight covers approximately 19 kilometers. The Dewey is approximately 19 kilometers from the propulsion section's final SM-6 intercept point. The propulsion section of the YJ-21 passes 48 meters above the Dewey's flight deck at 2:33:41 a.m., traveling at approximately Mach 3.8, generating a bow shockwave of approximately 3.2 atmospheres overpressure that arrives at the ship's surface in the same fraction of a second as the acoustic wave from the object's passage. The crew experiences it as a single event. a horizontal pressure wave striking the ship from above and to port simultaneously, lasting 0.09 seconds, followed immediately by the sound. Not the sound of impact, but the sound of air compressed ahead of a Mach 3.8 object at close range. A crack boom that begins and ends faster than the inner ear can process it as directional. Everyone on the ship who is not actively braced against a structural member goes sideways in that 0.09-second impulse. The Dewey's hull responds as designed. The structural steel absorbs and redistributes the loading. The frames flex slightly, and the ship settles back to her normal waterline. Nothing is on fire. Nothing is flooding. The ship's systems continue operating without alarm. The combat systems officer reports in CIC at 2:33:52 a.m. SPY-1D nominal, VLS nominal, Aegis nominal. No damage indications. The officer of the deck conducts a verbal walkthrough with all watch stations. All stations report nominal. The engineering officer of the watch reports no alarms, no fault indications. All systems operating within parameters. The commanding officer acknowledges. The engagement is complete. The ship is operational. The crew begins a post-engagement assessment that is routine in all aspects. The post-engagement assessment proceeds normally for 4 minutes and 37 seconds. At 2:38:29 a.m., the SPY-1D radar, which has been running continuously since the engagement began and has reported nominal throughout, produces a track classification on the tactical display in CIC that the combat systems officer immediately recognizes as anomalous. A surface contact at bearing 260, range 14 miles, classified by the Aegis track algorithm as a high-speed surface vessel, has appeared without any prior track history and is showing a speed of 63 knots. The systems officer queries the track. The SPY-1D confirms, bearing 260, range 14.2 miles, speed 63 knots, RCS consistent with a patrol vessel. He looks at the track for 4 seconds. No surface vessel in the South China Sea moves at 63 knots. He queries the track a second time. The track data changes. Bearing 261, range 14.1 miles, speed 71 knots. The speed has changed between 2 consecutive radar sweeps in a way that would require approximately 8 g of lateral acceleration. Nothing surface capable achieves 8 g. The systems officer picks up the sound-powered phone. Engineering, CIC. We need a full SPY-1D calibration check. I have a phantom surface track that is showing non-physical behavior. This is symptom 1. The second symptom presents itself at 2:41 a.m. The Dewey's fuel management system, a passive monitoring system that logs JP5 fuel consumption across both engine rooms and provides running calculations of fuel state, reports a discrepancy between the calculated fuel consumption based on engine operating data and the measured fuel level in tank C4, a 12,000-gallon capacity JP5 tank on the port side of the ship at frame 54, second deck. The measured fuel level in C4 is dropping 0.3% per hour faster than the consumption calculation predicts. 0.3% of 12,000 gallons is 36 gallons. 36 gallons per hour is 0.6 gallons per minute. An unaccounted fuel loss of 0.6 gallons per minute is within the noise band of the fuel management system's sensor accuracy. The system's documentation specifies a measurement uncertainty of plus or minus 0.5%, and a 0.3% deviation is within that band. The engineering officer of the watch logs the discrepancy, annotates it as within sensor tolerance, and moves on. He does not mention it to the chief engineer. The chief engineer is not in the engineering spaces. He is on the bridge, conducting the post-engagement walkthrough with the commanding officer. The third symptom presents itself at 2:44 a.m., and this one is not subtle. The EW operator reports an anomaly not related to the external environment. The ship's own SLQ-32 is generating an internal spurious emission at 9.3 GHz within the SPY-1D's operating frequency range, appearing on his waterfall display as a frequency line that matches no external emitter. An internal SPY-1D emission showing up in the EW receiver means the phased array is generating RF side lobe energy at angles outside the main beam. This happens when the phase shifter elements are not operating in calibrated synchrony. When some elements are shifted out of phase, causing side lobe leakage at uncontrolled angles. The SPY-1D's phase shifter elements have been disturbed. Not catastrophically, not enough to trip the built-in test system's fault threshold, but enough to generate phantom surface tracks at non-physical speeds and to create side lobe leakage that the EW system is picking up as a spurious internal emission. The EW operator reports it to CIC at 2:44:09 a.m. The systems officer now has two data points: phantom track at 2:38 a.m., internal spurious emission at 2:44 a.m. Both are consistent with a single cause: partial miscalibration of the SPY-1D following the 0.09-second shockwave loading at 2:33:41 a.m. The shockwave deformed the forward superstructure by a sub-alarm amount. The strain sensors logged a 0.003% deformation. Within the design envelope, auto cleared, but 0.003% deformation at the SPY-1D array mounting points shifts the array's physical orientation by a fraction of a millimeter, which changes the inter-element phase relationships. The radar is not broken. The radar is mispointing by an amount too small to alarm and too large to produce accurate fire control solutions. The systems officer reports to the commanding officer at 2:45 a.m. Captain, I assess we have SPY-1D phase calibration drift from the overpressure event. The radar is operational, but I cannot confirm fire control solution accuracy. We may be in a degraded engagement capability status without knowing it. This is the problem that has no alarm. The status board in DC Central shows all green. The SPY-1D shows active and nominal on its own built-in test. The ship looks undamaged. By every sensor checking for damage, there is no damage. But the sensor doing the looking is the sensor that has been affected, and a sensor cannot reliably assess its own miscalibration. The chief engineer arrives in DC Central at 2:46 a.m. and reads the green board. He does not accept it. A ship overflown by a Mach 3.8 object at 48 meters does not have a green board. He pulls the raw data logs, not alarm status, not fault indicators, but raw sensor values. Structural strain gauges, compartment pressure monitors, pipe pressure monitors, fuel management system, and reads them the way a diagnostician reads a chart, looking not for out-of-range values, but for trends, for values moving when they should be stable, for discrepancies between calculated and measured quantities. He finds 4 anomalies in 12 minutes. First, the fuel level discrepancy in tank C4, 0.3% per hour below calculated consumption, within sensor tolerance, but consistent with a small fuel loss from a microfracture in the C4 tank boundary. Second, the bilge level in the port engine room, at frame 52 to 56, is rising at 0.4 inches per hour above its baseline. Not alarming. The bilge accumulates condensation and minor seepage under normal operations, and 0.4 inches per hour is within the range the pump management system handles automatically without flagging. But the rate has increased by 0.4 inches per hour compared to the pre-event baseline logged at 2 a.m. Third, the pipe pressure monitoring for the seawater cooling supply loop serving the forward GTG heat exchangers shows a 2 psi pressure drop compared to the 2 a.m. baseline. Not enough to alarm, consistent with a small leak in the supply loop, or consistent with normal sensor drift. But combined with the bilge level increase in the same frame range, it is consistent with a seawater cooling pipe microfracture between frames 52 and 56. Fourth, The SPY-1D phase calibration log, pulled from the radar's own internal diagnostic archive, not the alarm log, but the raw calibration values updated every 90 seconds, shows that the inter-element phase reference for array phase 2 has drifted by 0.0034 degrees since 2:33 a.m. 0.0034 degrees. The alarm threshold is 0.01 degrees. The current drift is 1/3 of the alarm threshold. Not alarming, but trending. Each 90-second calibration cycle shows the same direction of drift, consistent with a slowly relaxing mechanical deformation in the array mounting structure. The chief engineer lays the 4 anomalies out in his notebook with the timestamps. They are not individually significant. Together, and aligned to the 2:33:41 a.m. overpressure event, they describe a ship that has sustained distributed micro damage across at least 3 systems simultaneously. The fuel tank boundary at frame 54, the seawater cooling pipe between frames 52 and 56, and the SPY-1D array mounting structure. With a 4th system, the radar calibration, in active slow degradation. He takes this analysis to the commanding officer at 2:58 a.m. and presents it in 3 sentences. The ship has sustained distributed micro damage that does not appear in any alarm system. The SPY-1D phase drift is progressive and will reach the alarm threshold in approximately 6 hours unless the mounting deformation is stabilized. And there is a fuel loss and cooling water loss in the port engine room vicinity. That, if not located and addressed, will produce a compounding problem when the rate of loss increases as the microfractures propagate under operating pressure cycles. The commanding officer asks the question that the commanding officer always asks. What do you need? The chief engineer says he needs to find 4 things that are leaking things they are not supposed to be leaking, in a ship that has no indication any of them are leaking. The diagnostic operation begins at 3:02 a.m. and takes the form of something the crew has a term for, borrowed from submarine operations. A field survey, not a damage control response. There is nothing to respond to yet. A systematic, compartment-by-compartment physical inspection of every space in the frame 50 to 60 range, with the inspectors looking not for visible damage, but for the physical indicators of micro damage. Moisture where there should be no moisture. Fuel smell where there should be no fuel smell. Thermal variation in pipe surfaces indicating differential temperature from a micro leak. And hairline fracture patterns in welds and fittings. The team is 4 people. 2 machinists' mates, 1 hull technician, and the chief engineer, working in pairs with UV inspection lights and combustible gas detectors, covering 12 compartments systematically. The fuel microfracture is found first at 3:09 a.m. The hull technician working the port's second deck void space at frame 54 detects a JP5 smell at the outboard tank boundary, a kerosene and solvent odor that trained personnel can detect at concentrations too low for most monitors to flag. He traces it to the inboard face of the C4 tank boundary plate, a 7-centimeter hairline fracture along the weld seam at the tank's lower boundary, weeping fuel that is evaporating before reaching the bilge, which is why the bilge monitor has not flagged contamination. The vapor is accumulating in the void space instead. The combustible gas detector reads 6% of the lower explosive limit. Not alarming. Trending upward, the seawater cooling pipe fracture is found at 3:17 a.m. The machinist's mate, working the port engine room spaces between frames 52 and 56, finds fresh moisture on the insulation wrap of a 3-inch seawater cooling supply line. He removes a section of wrap and finds the source. A hairline circumferential crack in the pipe wall at the bracket weld, approximately 40% of the pipe circumference, seeping at a rate consistent with both the bilge level increase and the pressure drop on the supply loop monitor. A 40% circumferential crack at 45 pounds per square inch will not fail immediately. The propagation timeline is 4 to 6 hours under normal conditions. But normal conditions does not include the vibration loading of 2 LM2500 turbines running in the adjacent machinery space. And the propagation rate under operating vibration will be faster. The SPY-1D array mounting deformation is assessed at 3:24 a.m. by the systems officer and the electronics technician, using the physical inspection protocol for the SPY-1D mounting structure. The forward array mounting frame, a welded steel structure that interfaces the array face with the superstructure, has a hairline fracture at the lower starboard mounting gusset, running approximately 60 millimeters along the weld seam. The gusset is one of 8 structural connections between the mounting frame and the superstructure. The hairline fracture in one gusset reduces the mounting stiffness by approximately 12%, which is why the array has been slowly drifting in its mounting position under the dynamic loads of the ship's motion. Each wave impact transmits a small oscillatory force through the hull structure to the mounting frame, and the fractured gusset allows a small additional deflection of the array face, which has been progressively accumulating as phase drift since 2:33 a.m. The bilge level increase is now understood as composite. The seawater cooling pipe contributes approximately 0.3 inches per hour. And a secondary find, a micro fracture in a 2-inch condensate return line at frame 53, contributes 0.1 inches per hour. The chief engineer has his 4 sources. He briefs the commanding officer at 3:28 a.m. 2 pipe fractures repairable with standard materials. 1 fuel tank boundary fracture requiring epoxy patch and vapor ventilation. 1 structural mounting fracture requiring mechanical restabilization. None are emergencies in isolation. Together, unaddressed, they produce combustible vapor reaching the alarm threshold in 3 hours, a cooling pipe failure in 4 to 6 hours reducing GTG heat exchanger capacity, and an SPY-1D phase drift reaching the alarm threshold in 5 hours, while producing progressively degraded fire control solutions in any engagement that occurs before it gets there. The ship is fighting a problem that looks like it has been resolved. The status board says green. The engagement is complete. The tactical picture shows no immediate pressure. But inside the ship, in 3 separate compartments in the frame 50 to 60 range, 4 microfractures are quietly doing what microfractures do, widening. The repair sequencing is set by time to failure and consequence. Fuel tank boundary first, shortest vapor timeline, most severe ignition consequence. Seawater cooling pipe second, longer timeline but catastrophic failure mode. A pipe rupture flooding the engine room with seawater. SPY-1D mounting third, a ship that cannot trust its radar, cannot defend itself, and does not know it. Condensate return line last, bilge contribution minor and manageable. The fuel tank boundary repair is a welding operation under normal circumstances. Welding on a fuel tank boundary is not a normal circumstance. The tank is full, and the adjacent void space has combustible vapor at 6% LEL. Welding produces sparks. The chief engineer does not weld. He uses a 2-part marine epoxy rated for fuel service, applied cold, which can seal the hairline fracture at the weld seam without any ignition risk. The technique is identical to the wet surface application used in the Arctic event 3 months prior on a different ship. But this crew has not done it. The hull technician has. He learned it at a DC cross-training session. He knows the procedure. Heat gun displacement of the surface vapor layer. Mixed epoxy applied to the dry zone before vapor rediffuses. Manual pressure held during initial set. He begins the application at 3:34 a.m. Before he begins, the void space is ventilated for 6 minutes by opening the upper access panel and directing a portable fan across the space, reducing the vapor concentration from 6% LEL to 2% LEL before any tools are brought in. The heat gun is not a spark source. The epoxy application is non-sparking. The manual pressure phase takes 3 minutes and 40 seconds at the weld seam. The fuel weeping stops. The void space vapor concentration, measured again at 3:42 a.m., reads 1% LEL and declining as the ventilation continues. The seawater cooling pipe repair is a speed patch installation. The circumferential crack is ideal for the rubber sheet and C-clamp approach, and the patch installation takes 8 minutes by the machinist's mate who found the fracture. The seawater cooling supply pressure recovers to 46 pounds per square inch after patch installation. Still 1 pound per square inch below the pre-event baseline, likely because the patch slightly reduces the pipe's internal volume, but within the operating envelope for the heat exchanger cooling function. The bilge level in the port engine room begins dropping as the P250 pump removes the accumulated seepage. The SPY-1D mounting fracture repair is the most technically complex of the four. The fractured gusset is a structural steel member that would normally be repaired by welding. Re-welding the fracture seam, adding a doubler plate over the weld, testing for full load transfer. Welding on the array mounting structure while the array is operational is not permitted. The thermal input from welding would cause local deformation in the mounting frame that is worse than the fracture it is repairing. The array must be taken offline for the mounting repair. The systems officer and the chief engineer work this through together. If the array is taken offline for mounting repair, the ship has zero radar coverage, no surveillance, no fire control during the repair period. In the South China Sea, with the Fujian Coast Battery still active and the post-engagement period being the time of maximum secondary engagement risk, zero radar coverage is not acceptable. The alternative is mechanical restabilization without welding. A mechanical clamp across the fractured gusset to restore the missing load path. Without thermal input, without taking the array offline. No off-the-shelf clamp fits the gusset profile. The chief engineer looks at the geometry for 90 seconds, goes to the DC equipment space, and returns with 2 heavy-duty stainless steel hose clamps and a section of 4mm steel bar stock. He cuts the bar stock to length and bends it against the gusset itself as a forming template. The formed bar bridges the fractured weld seam. 2 hose clamps tighten across the bar and the gusset simultaneously, restoring mechanical continuity across the broken weld. Installed without taking the array offline, without welding. Installation time, 22 minutes from concept to torqued clamps. The SPY-1D phase drift, logged every 90 seconds, stops progressing immediately after the clamp installation is complete. The array mounting frame is stable under dynamic load. The calibration drift does not reverse. The accumulated 0.0034 degree drift from the past 90 minutes of slow deformation is still present, but it stops accumulating. The systems officer schedules a full radar calibration at 0600, 2 hours before the start of the next anticipated activity window, which will restore the SPY-1D to its pre-event accuracy baseline. By 4:07 a.m., 94 minutes after the Mach 3.8 propulsion section passed 48 meters above the flight deck and was classified as no damage. All 4 microfractures have been found and addressed. The vapor concentration in the port void space reads 0.8% LEL. The seawater cooling pipe patch is holding at 46 pounds per square inch. The SPY-1D mounting clamp is loaded and stable. The bilge level in the port engine room is below its pre-event baseline. The status board in DC Central has not changed from green since the engagement ended. There has been nothing to change it to. The ship's alarm systems have not triggered once in the 94 minutes of diagnostic work and repair. The crew did not respond to alarms. They responded to 4 raw data anomalies that individually meant nothing and collectively meant that the ship was failing in 4 places without knowing it. 1 YJ-21 propulsion section, 340 kilograms, passed 48 meters above the flight deck at Mach 3.8. Shockwave overpressure, 3.2 atmospheres for 0.09 seconds. 0 alarm threshold events detected post-incident. 4 microfractures identified through raw data trend analysis. C4 fuel tank boundary weld. Seawater cooling pipe frame 54. Condensate return line frame 53. SPY-1D array mounting gusset. Combustible vapor concentration in port void space peaked at 6% LEL. SPY-1D phase calibration drift reached 0.0034 degrees before mechanical stabilization. All 4 fractures addressed within 94 minutes of the overpressure event. Radar calibration scheduled for 0600. Full radar accuracy restored before the next engagement window. Ship status operational. The post-event report filed by the commanding officer contained one sentence that the fleet's engineering community subsequently circulated as a formal training reference. The most dangerous damage a ship can sustain is damage that does not appear in any alarm system, because the crew will not know to look for it unless they understand what the ship should be doing and notice what it is actually doing instead. The difference between those two things: in the 94 minutes after a Mach 3.8 flyover of the South China Sea was the chief engineer's notebook and 4 anomalous numbers that were each, individually, within normal operating tolerance. That is what knowing a ship means. Not reading its alarms, reading its silence.